Okay, here we're going to look at modifying a binary search tree in both Racket and Java. So here was our binary search tree algorithm that we talked about before, and I want you to try and write insert in Racket. Even if you've seen the solution to this before, it's really good practice to try and write it out. It can help you get comfortable recursing through the tree structure. And actually that Racket code is going to be helpful pseudocode for writing the Java, which tends to be a little bit more verbose and a little harder to understand. Okay, so pause it and try and write insert in Racket, and pause it and try and write put, which is just insert, in Java. And I'll give you one more reminder. When we were doing it in Java, when we were doing things in Java in general, we were going to use a helper method to keep track of where we were in the BST. So here the size method shows that I'm keeping track of current node. So as I'm walking through the binary search tree, that current node is keeping track of where in the tree I am. Okay, try and write insert in Racket and Java, and I'll keep going. Okay, another video, live codes insert. So here we'll just walk through it. If I've got an empty binary search tree, then I make a new leaf. If E, the thing I'm trying to insert, is equal to the key, then I just return my current binary search tree, and that might be the root of a really big subtree, sort of doesn't matter. It's already in there. We don't need to change anything about that structure. Okay, now if E is less than the key, then it should go in the left. And instead of only making a recursive call on the left subtree like we have here, I also have to make a new BST, because in Racket we can't change the contents of any of our lists. And since binary search trees are represented as lists, whenever we need to change anything inside of one of those, we have to actually make a whole new one. That's why here, and again, when I want to insert it on the right, I have to make a new binary search tree. Give it the key again, give it the right tree again that hasn't changed, and then give it this updated left tree. And we're going to look for this same idea in the Java version. So for the Java version, we're going to use that same structure where we have the main method that someone's going to call, that's put. And then we're going to have a second version that's going to be our helper. And in addition to taking in the key and the value, it's also going to take in this BST node temp root. And maybe I'll just call it node. I want us to talk through that case similar to we saw in Racket with the empty tree. So say in my put method, I call put with the key and the value and this dot root node. Now imagine root node is null because it's an empty tree. Inside of the put method, I'd be like, oh, yo, if node is equal to null, so if node is equal null, then I need to make a new binary search tree node. So new BST node that's going to have input key as the key and input value as the value. But imagine, okay, it's directly called from the original put. I get here, it's null. Well, like, how do I get whatever's returned to change the actual tree? I need to return this new binary search tree that I make. And up here, whatever's returned, I need to save as my new root node. And to make it a little easier to distinguish, I'll call this put H for put helper, or maybe even just put helper. Okay, so put is going to call put helper. It's different because it also takes in that root node, so it's going to keep track of our current node. If node is null, then we're going to return a newly created binary search tree node, and put is going to save that as the new root node. So I hope it's clear that this put helper really needs to be returning that BST node. And you can see at the bottom of the original put that we return the value. So we're implementing the map interface, and in the map interface, the put method returns the value that you've added. So we're just returning it. We're not modifying it at all. Okay, let's dig into the put helper a little bit more. So we have 3 cases now. Those cases are that we're at the correct node, and then we need to go to the left or go to the right. Okay, how would we know if we need to, if we're at the correct node? That would mean that if node dot key, if that thing is equals to the input key, then I'm at the right node, okay? I already have the key that I'm trying to add. It's already in my tree. And what I need to do now is I need to update the value that I have associated with that node. So I need to say node.value. It needs to get this new input value. And you can think about it as like, oh, put helper is done then. It's updated the value. But the really important thing is, remember, put helper needs to return the current BST node. So here we need to return node. And you can imagine us calling put where we we have a tree with just one node. That's the root node. We pass it here to put helper. We find that the key is equal to the input key. We update the value and we return that node. And we needed to reset root node to be that thing. And you're like, oh, Colleen, that's actually not necessary in this case because the actual node didn't change. And that's correct. But because in the case where we're creating a new binary search tree, we need to return a BST node and set any elements that should be referencing it, we need to do the same exact thing here. And we'll see later on in our code where that comes to play. Okay, how do we know if we should go to the left? And here I wrote a method in order keys so that I don't have to worry about what compare to does. So this will tell me true or false if the two arguments that I pass in are in order. So let's call that. So if in order keys, and I should go to the left if input key is less than the node's key. If those two things are in order, then input key is smaller. And for go to the right, I can just say else. Okay, let's look at what we should do if we should go to the left. We know that we're going to call put helper with that same input key and the same input value. But the node, now we want to call it on the left tree. So we know we need to call put helper. But what about the case where node.left tree is null? Then it's going to create an all new node for our left tree. And we need to make sure that we save that somewhere. So in the case where this recursive call hits this base case where node is equal to null, it's going to make a new BST node that we need to be referencing. So we need to be able to say node.left tree should be whatever put helper returns. And then again, we need to return that node. Okay, similarly, when we go to the right, we need to reset the right subtree to be whatever put helper returns, and we're going to pass it the input key and the input value, and then the node dot right tree, and then return node. Oh, and I can see that in 3 of these cases, I'm returning node. So let's refactor this, and I'll turn that into an else if. Then I can clean this up so that I just return node at the very end. But it's really important that you understand why I have to set left tree and why I need to return node every time.